Hello there, another short video we're going to post to YouTube for this upcoming weekend. This is the map that we ended off with as we started to talk about our air masses and developing the concept that between these air masses, areas where we might have warm, moist air meeting up with colder, drier air, again, not nearly always as extreme as what we see here, but still something where we're going to have to separate them via what's known as a frontal boundary. And so in this example here on the schematic where we ended off with on the last video, you can see a cold front draped from, northern Missouri down in the Gulf Coast, a stationary boundary from that low extending north-northeastward into southern Canada, followed by another cold frontal boundary north of that. In fairness, there are a number of issues with this schematic. I will leave it at that, and we will try to here and there focus back on some real data to help supplement this, and we'll spend a little bit more time in class as well, likely on Monday, pardon me, looking at the homework, and again, trying to assess how to do these isoplus, lines of equal pressure, and also to look at where frontal boundaries may exist. And so if we get the screen set up right, we transition down into fronts. And transition is a great word here because fronts are here a transition zone between two air masses. And so on the last screen, again, we have the maritime tropical air mass with the incoming continental polar air mass. And the reason we know that, and we'll get into it, is for instance, you see the blue line with the blue triangles pointing towards Missouri and Arkansas and Louisiana and pointing towards that warm, moist air mass. Again, the orientation of these little pips along the front is indeed important. And that suggests that this cold air mass is making progress into your warm air mass. The frontal boundary is moving in the direction of these little pips, and we'll establish that further moving forward. And so the overall idea here first is how do we identify fronts in general? Fronts are going to be identified first and foremost and most easily under most circumstances, that was a lot of mosts, for a sharp temperature change, which you saw on that schematic, and we will try to find under a number of examples in real time. Again, mind you that the real world rarely operates as well as a schematic. And so where we see cold temperatures and warm temperatures near one another, that may delineate a frontal boundary. Sharp changes in dew point. Again, understanding that air masses are going to be characterized by their temperature as well as their moisture. This means that if we have a sharp decrease, for instance, in dew point, you may be getting into a colder, drier air mass. Or, since we continue to talk in the cold frontal perspective, maybe the idea that we have some drier air that is rapidly replaced by some more muggy air mass. And that might be a warm frontal boundary that passed through your region. A shift in wind direction. We'll talk a little bit again, but this goes back to what we talked in class this week with regard to the counterclockwise motion around a low in the northern hemisphere and vice versa around a high. So since most of these frontal boundaries are going to have some connection, maybe distance away, to a low pressure system, we can utilize that information and maybe suggest southerly winds in a maritime tropical air mass, and then a transition to northwesterly winds helping to mark a frontal boundary passage. Pressure changes. We'll get a little bit more into this periodically moving forward, but the general concept is we can see tendencies in pressure associated with fronts. You may recall this from the lab that we did on station models, and one of the things that was off to the right of your station model center was pressure tendency, the increase or decrease in pressure over the last number of hours. We do oftentimes find lowest pressures, or these kinks in the isobars. Understanding that's not really easy to grasp at this point, but we'll get there. You may associate those with a frontal boundary, and then, for instance, if a cold front does pass your area, a relatively rapid rise in pressure after the boundary has passed an area. And clouds and precipitation. Clouds and precipitation are kind of a fuzzy thing for identifying fronts. What really happens as we start to identify fronts in meteorology is we look for combinations of these factors. For instance, you may start off by trying to look for a sharp temperature change and then fine-tune the location of your boundary based upon where the dew point changes or where the wind direction changes. And sometimes clouds and precipitation can be a very valuable asset in helping to fine-tune where the front might be located. Other times, not so much. You may have a large expanse of clouds and precip, for instance, ahead of a warm frontal boundary, and that's going to be related to the slope of the boundary as we'll get to, well, in class next week. And so here you go. Got a little bit ahead of myself there, the idea that you can use multiple traits to fine-tune that frontal position. And so let's bring up that map that we had, again, the other previous video. Again, I'm actually recording this in the wee hours of the morning on Friday, but it's often easier to identify these boundaries as you look towards afternoon hours. And so let's continue to look here in the Midwest. None of the boundaries are super well defined at this period. And so we're going to zoom in here a little bit more on this boundary that's draped across the upper Great Lakes. So northern Michigan, down through Wisconsin, southern Minnesota, and then connected here to a low pressure that they've identified here across eastern Nebraska. And so if we zoom in a little closer and we look at the area, say for instance across, well, let's focus in on Wisconsin, our neighbors to the northwest. South of your boundary, again, we would not have described this as a muggy air mass on Thursday afternoon, but it was definitely warm for the season. You can see temperatures down here in the mid-70s, extending into the mid to upper 70s here around Milwaukee. Dew points near 60, so not dry by any stretch of the imagination, but also, again, not what you'd consider the muggy 65, 70 dew points that we talked about when we discussed heat index. North of the boundary, our temperatures drop from these mid-70s into the low 60s. Again, not the sharpest boundary, but still a pretty notable temperature contrast. One thing that does often make things difficult here in the Great Lakes is, for instance, you can see this observation here, which I'm pretty sure is Sheboygan, Wisconsin, 61 degrees, but your wind direction is actually off of Lake Michigan, so that would have been causing some type of cooling effect likely on this afternoon. Looking at wind direction, for instance, southerly winds. Generally speaking, at least a component to the south, maybe a little more south-southwest as you get down here in Illinois. As you move north of the boundary, more of an east stretching to a northeasterly type flow. So that wind shift that you note as well. Dew points, again in this example, actually are not much of a help. Upper 50s, low 60s, upper 50s, low 60s. Sure, as we get up here into Canada, they're dropping into the mid-30s, but you're starting to get a large distance away from your boundary. Here we can at least note that north of our boundary, a little bit more in terms of cloudiness here across northern Wisconsin. And then you can even see some light rain showers that may have been occurring up here somewhere near Rhinelander. Don't hold me to that exact location. And so again, a lot of things that we can note. If you look here at this, for instance, one isobar here, this looks to be, if I zoom in, our 1012 isobar here. You can notice that there's this little kink in the pressure where this low is. And we oftentimes are going to try to draw these boundaries through these kinks in the isobars. This is what we talked about there. In fact, if we continue to track this one up here towards New England, you can see again another isobar up here, and where it kinks we find that cold frontal boundary located. And so again, just trying to look at a number of different features. I guess it might be also interesting if I zoom back out a little bit, to kind of take a little bit of a refresher on winds and the pressure gradient as well. So one thing you can note is the eastern United States, we do not see a lot of these isobars or lines of equal pressure. In fact, you see one here, another here, and another here, very widely spaced across much of the eastern United States. What does that correspond with? 5 knots, 5 knots, 5 knots, maybe 10 knots. 5 knots, weak winds across a large portion of the country here. Let's look here towards, say the lee of the Rockies here in the Dakotas. Isobar, 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 isobar. You're much more closely packed here in the southern, let's say the southern prairie of Canada. It's extending back towards the Rockies. 20 knots, 20 knots, 20 knots, 20, 20. Much stronger winds again where these isobars are closely packed. The other thing is, especially in here, you can notice this cross isobar component. Basically a generally southerly wind right here, crossing at about, there you go, 30 degrees to your isobars because of that friction. Little bonus topic to bring up here during this video. All right, we're going to crank through a few more slides here on the cold front, and then we will call this a morning. So here your cold front, important. When we talk about frontal boundaries, we talk about them as what is replacing an existing air mass. So for example, when we talk about a cold front, the air mass that is advancing, that is doing the replacing, is the cold air. So here the cold air is replacing warm air. This is important because you'll notice it's different when we get to things such as warm fronts. And so in this example, and again, most commonly we're going to find continental polar air displacing maritime tropical air when we talk about large areas of the United States. We're going to signify these by a blue line with blue triangles, as I indicated earlier on our schematic, and those triangles are going to point in the direction that the front is moving. So here we see a boundary in the schematic draped across Tennessee, just clipping northern Mississippi and back into Arkansas, and this boundary would be advancing into southern Tennessee, northern Mississippi, and northern Alabama due to the orientation of our blue triangles. We oftentimes get showery precipitation, maybe some thunderstorms, squall lines may be associated with these areas where we get more concentrated thunderstorms, may be severe with some stronger winds. In fact, even though it is just a schematic, you can note in this diagram across northern Mississippi, this little thing that looks like kind of an R, a thunderstorm symbol for this location here in Mississippi. And so again, the idea that cold fronts are typically going to be associated with the most intense temperature gradients. Again, there's that word gradient again. And so cold air here, 30s, not a very pleasant day across Tennessee and Arkansas north of the boundary. But here, rapidly shifting about 10 degrees, rapidly shifting 12 degrees, both sides of that boundary. And the general air mass much further north, mid-20s, well south, upper 50s. But that sharpest contrast is going to occur right near your boundary. Notice again here in the schematic, they're orienting it right through this pressure trough where we see these little kinks in the isobars. The wind direction, northwesterly to southwesterly, isn't going to be a 180-degree difference, but again, a sharp change in wind direction can be found along these stronger cold fronts. And so what's happening with these pressure troughs is that as the cold front approaches, pressures are going to lower and then increase after the front is passed. So here you can see 1010s, 1013s, dropping to about 1007 right along that boundary and then increasing back to about 1013. Is this always going to be the case? No, but it is definitely something that you can find. One thing that we'll discuss a little more in class is the fact that cold fronts are often much easier to identify than warm fronts or quasi-stationary boundaries. One of the trickier concepts to grasp with regards to fronts is that we view our maps as two-dimensional. It's the natural way of doing things. But in reality, frontal boundaries are going to be three-dimensional in nature. And so what you have here is this plane here trying to orient to the surface, is showing the surface motion of your boundaries. These P's are showing pressure lines and again showing the little kink there. The boundary here is designed to be moving from the left side of your screen to the right side of your screen. And so what's happening here is this cold air is more dense than the warm air. You can note that along this boundary it's a pretty sharp change in the vertical. So in other words, this cold air mass is kind of a wedge pushing both along the surface but also aloft here, showing up to maybe a few kilometers in the atmosphere. And this continental polar air mass is pushing through the more dense cold air, is why this boundary has the ability to move relatively rapidly. And it has the ability to push this maritime tropical, this warmer, less dense air mass upward. And so you can here see a CB symbol that's going to indicate those cumulonimbus, those clouds of vertical nature that can produce thunderstorms. And, well, this is trying to indicate rain and even potentially a squall line as this frontal boundary moves off to the, well, we'll say left side of the screen. I don't want to presume that it's east. So again, this is going to be one of those things we have to keep in mind, is that they do have a vertical component that becomes quite critical to help understand the weather associated with our boundaries. Again, looking at that vertical component to our width, or a vertical component to our front, here you have the frontal boundary again moving from left to right across your screen. Not always are your thunderstorms going to be along and ahead of the front. They can trail your frontal boundary as well. And so the big thing again to take away as we look at this different view is this warm moist air, this maritime tropical air mass gets lifted up, it gets lifted up, it gets lifted up, and it may take a while for us to reach a point where this air becomes saturated. As you get higher and higher up, you're getting to cooler and cooler temperatures, so you may get some mixed precipitation higher up in a cloud. We're going to get a lot into that as we move into precipitation. And so Here you even get a bonus lightning bolt in the schematic, showing that you get a lot of vertical lift with these storms. This will also become important as we move into stability. And so just another interesting feature to keep in mind, this sharp wedge of air. And so again, the fact that this has a steep slope relative to what we'll see later on in warm fronts is a critical thing with the cold frontal boundary. And so this is an example of a squall line, which you have going on here. An area that's concentrated along your boundary oftentimes. Yeah, there's a lot of variability to these. They can move pretty far ahead of a frontal boundary as well. But what you have here is right along that frontal boundary where you're having that strong lift because of that cold, dense air here to the north plowing towards the southwest. We cause this maritime tropical, this moist, warm air to rise, and here we got some darker reds indicating stronger thunderstorms with this squall line feature. And so we'll end with a little bit of a different setup here, a backdoor cold front. Not every cold front is always going to move from northwest to southeast. That's what most schematics will show, and in fairness, that's what the canonical setup is, especially across the Midwest and much of the areas east of the Rockies in the United States. But here we have to keep in mind that that maritime polar air is another one of our air masses. Not one that we regularly deal with here, say around Chicago and Valpo, although there are some similarities to those lake breezes that we get in summer where it's in the 90s and it rapidly crashes into the 70s, especially if you're, say, a little closer to Chicago and the lakeshore. Maybe not as much here in Valpo, but maybe as you get north here closer to the dunes. And so in this example, that cooler maritime polar air, again, maritime, it's going to have some moisture characteristics, but it's going to be chilly because of its source region across the North Atlantic. And that can surge in a backdoor nature, moving southwest, and oftentimes meet up and create some thunderstorms here in areas that are highly populated. In fact, although not necessarily important to know for an exam or anything like that, what you can have with these scenarios is a little bit of a surprise setup at times that can create havoc for some of these very large airports, say even Boston Logan, down towards LaGuardia, areas such as Philadelphia and Newark. A lot of highly populated areas in here can be affected strongly by one of these backdoor cold fronts. So we'll call it a day. This went for a little bit longer than expected. Hopefully this was helpful to kind of get a little bit of refresher on winds as well. Hopefully you have the chance to review these before class on Monday. We will go over a little bit more about, again, why are fronts called fronts, transition into warm frontal boundaries, and be able to spend a little bit of time going over assignment number 2 as we meet on Monday. Otherwise, if you are viewing this on Friday or Saturday, enjoy this beautiful maritime tropical air mass that you have. Again, we may push into the 80s both days before we look at a cool off by middle to end of next week. That's going to be quite notable, and so we'll spend a little time chatting about that as well. Take care and stay healthy. See you on Monday.